Okay, let's talk about a very useful digital logic circuit called a half adder. And a half adder will perform these binary rules of addition. As you can see here, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 2, which in binary is 1, 0. So what we're going to do is take these binary addition rules, put them into a truth table to see what logic circuit will give us a half adder. So to put these rules into a truth table, I'm going to label this top row as variable A, and this next row is variable B. In the result, we're going to label the furthest to the right bit, which is the least significant bit of the result, as S, and we'll label the bit just to the left of the least significant bit the C bit. And I realize I don't have to put the zeros here, but I will just to make it clear what the C output equals in these cases. Okay, because we take the result as being an output, and we take what we're adding, these bits that we're adding, as the input. So now with these bits all labeled, I'm going to make a truth table from those rules. A and B are inputs, and C and S are outputs. So this first rule, A and B both 0, gives a result of C and S both 0, A 0, and B 1 gives a result of C 0, S 1, A 1, B 0 gives us C 0, S 1, and when both A and B are 1, we get a C output of 1 and an S output of 0. So you see this truth table came from these rules. So now from this truth table we can come up with the logic circuit that we need, and that logic circuit will perform these binary addition rules. So you should be able to do this based on previous discussion. If you just look at the C output and compare that output to these inputs, you can see that the C output is only a 1 when both inputs are 1. So you should know what that gate is. And then to get the gate for the S output, well, its output is a 1 only when these inputs are different. So again, that's a gate that we talked about that you should be able to come up with. And that's part of what you need to do for lab 2. Okay, so I'll leave that up for you to do. Now, the half adder, it will perform these rules like we stated. However, most of the time when you're doing useful or meaningful binary addition, it's with multiple bit binary numbers. You know, this is just single bit addition here. But you know, most often you're adding you know, binary numbers that have more than one bit. They're multiple bit. For example, let's say you're adding two 4-bit binary numbers. Okay, as you know from previous discussion, this is a binary representation of 7 in base 10. Right, and this is a binary representation. Right, these are binary numbers. This is a binary representation of 6. Okay, so when we go to add multiple bit binary numbers, we add them column by column, just like when you're adding base 10 numbers that have multiple digits. So we start here with the least significant bit column. 1 plus 0 is 1. 1 plus 1 is 2, which is 0 with a carry of 1. And now we get to this column where we're adding 3 1s. Well, the half adder, it can't handle adding 3 1s because it only has 2 inputs. See, the schematic symbol for a half adder is typically this. It's just a box labeled HA where you've got your two inputs, A and B, and you've got your two outputs. And you might have already guessed this, I didn't write this, but you probably guessed this, that this carry here is a carry out. I just had it labeled C, but we could put a subscript 0 there now for carry out. So you see, in a situation like this with this multiple bit addition, where there's a need to add 3 ones, right? Adding 3 ones would give you a binary 3, which is a 1 with a carry of 1. Well, a half adder could not perform this, could not handle this, because again, there's only 2 inputs to a half adder, not 3. So that's one drawback of a half adder, is that it can't handle a carry out from a column in multiple bit addition like this. So what we do have is we have another logic adding circuit that's called a full adder. And a full adder does have a third input that's typically labeled CI for carry in. And this is the truth table for a full adder. And since there's 3 inputs, and we've seen this before, where if you want to find the values that you can obtain from binary digital inputs, well, the number of values is just equal to 2 to the number of bits you have. Right, so here we have 3 bits for our inputs, since there's 3 inputs, A, B, and carry in. So there's 8 possible combinations that we have for our binary information here on the input of the full adder. So the full adder, if all the bits coming in are 0, well, the full adder is going to output a 0. Anytime one of the bits to the full adder is equal to a 1, it's going to output a binary 1. So carry out will be 0 and S will be 1 anytime we just have one of the full adder inputs equal to a 1. So that's all these cases here. Here we have 2 inputs to the full adder equaling 1, so the output's going to equal a binary 2. Okay, same here, and also same here. And then this last one, this is the case we were talking about before, where now all 3 inputs are 1, so the output would be a binary 3, which is 1, 1. Okay, so this is the truth table for a full adder, and we can come up with a logic circuit for this full adder by putting this truth table into K-map. In fact, we can get the reduced circuit. So for the carry out, the K-map is going to look like this. This is our A, this is our B, and this is our CI. We got cell 0, 1, 2, 3, 4, 5, 6, 7. So for carry out, index 3, the output is a 1. Index 5, the output is a 1. Index 6, the output is a 1. Index 7, the output is a 1. All the other cells are 0. Okay, so now from this K-map you can come up with the reduced expression for carry out, the output carry out. And I'm going to leave that up to you to do, because again, this is part of lab 2. And then you can do the same thing for the S output. Right, cell 0, 1, 2, 3, 4, 5, 6, 7. So for the S output, let's see, what do we have? We have an S, or excuse me, a 1 in the index 1 cell, and also the 2 cell, the 4 cell, and the 7 cell, right? And the rest of the cells are 0. So this is the K-map for the S output, and notice you have single groupings of 1s that are diagonal from each other. So in the previous video we talked about this, that when you have a situation like this where you have single groupings of 1s that are diagonal from each other, it probably means you can after you write your expression for each of the single groupings, that you can do factoring and reduce down to either exclusive ORs or exclusive NORs. And again, since this is part of Lab 2, I'm going to let you go ahead and do that analysis. Now, one last thing is that I want to show you the logic circuit to actually go ahead and add 2 4-bit binary numbers. You know, earlier I gave the example of adding, you know, a binary 7 to a binary 6, and you know, when we do this manually, we add these two 4-bit binary numbers column by column. Well, the hardware that does the addition, okay, like this 4-bit adder, it also does the addition column by column, that you have an adding circuit for each column. So this 4-bit adder, it has a half adder for the least significant bit column, okay, the A0. This is the least significant bit column. And then for all the other columns, it uses full adders, right, where this furthest to left full adder, that's the most significant bit column. And of course, the reason why you can get away with a half adder in your least significant bit column is because you don't have to worry about a carry in. But all the other columns are going to need full adders, since there's a possibility of a carry in. So, you know, in this example here, you know, if this was our A input and this was our B input, you would have the least significant bits going into the half adder. So in this case, B0 would be a 0, A would be a 1, and then the next column would add the 1s and the 1s along with any carry in, which would be 0 in this case. And then these two would be 1, 1, and you know, this carry in of course would be a 1 here, and then these 2 zeros. So you know, we wouldn't get a carry out from the half adder, but there would be a carry out from this full adder, and there would be a carry out from this full adder, and then our result would show as we did manually. And this carry out is the resultant carry out, which, as you can see here, we didn't get a carry out from that most significant bit column. So just like when you manually add multiple bit binary numbers, you go column by column. The same thing with the hardware. The hardware needs an adding circuit for each column. So this is a 4-bit adder. If you had an 8-bit adder, the concept's the same. You could have a half adder for the least significant bit column, but with an 8-bit adder, you would need 7 full adders for the 7 other columns that you would need to do the addition. You know, a 64-bit adder would have 1 half adder and 63 full adders. Okay, so with this information, you should be able to get a good start on Lab 2.